Hi everyone, welcome back to MATA35. In today's lecture, we're going to be talking about constant coefficient homogeneous higher order linear ODEs. So that sounds like quite a mouthful, but basically we're going to be specifying down to a specific type of very common ordinary differential equation, one that appears very often in applications, and then seeing that there's actually a fairly easy way of solving those particular ODEs. Let's go to the next slide. So the first thing is, well, let's recall linear higher order ODEs. And since this is something you guys have already learned, I'm just going to double check that you guys know it and ask you guys to answer if the following things are linear, nonlinear, or both question mark or none of the above. And hopefully my updated Zoom chat bot works this time. Okay, so let's start with y double prime plus y prime plus y is equal to 5. Is this linear, nonlinear, or both, or whatever? Okay. So it looks like the overwhelming answer here is that this is linear. That is correct. What about this one? Y double prime plus y squared is equal to 5. And let me reset before you guys do that. Okay, yep. So that is nonlinear because of the y squared. Very, very good. Let's say y triple prime plus sine of x, y prime plus x squared y is equal to 5x. Let me reset. Now, is this linear or nonlinear? Okay, yep. So we're getting a bunch of A's. That is correct. How about this one? What about y triple prime plus sine y prime plus x squared y is equal to 5? Oh, wait, sorry, I just skipped ahead somehow. Yeah. So is this linear or nonlinear? Yep, okay, so you guys understand linearity and nonlinearity. Very, very good. Let me give one last one. Y triple prime plus sine x y prime plus, let's say, 5x squared y is equal to 5y. And let me reset. Is this linear or nonlinear? Okay, so it looks like this one, there's a bit more of a split between people. Okay, yes, because this one is slightly more complicated. So let's see what happens though. We can rewrite this function, we can rewrite this as y triple prime plus sine of x y prime plus 5x squared minus 5y is equal to 0. So this actually is linear. So you have to be a little careful because sometimes you can rewrite your ODE into a form that is linear, and when that's the case, the ODE is linear. Okay, so now let's go on to the next point. What does it mean for a linear ODE to be homogeneous or inhomogeneous? So if you write your function like this, so if you put it in this why is the second one last one linear? Okay, so let's walk through this again, just because it's important. So the point is that whether or not it's linear in x is irrelevant. The question is whether or not you have a single, you have a linear sum of the y's and y primes. And so the second one here is linear. Or sorry, the last one here is linear. Okay, but now let's move on to homogeneous and inhomogeneous. So once you've written in the standard form, it turns out if you have written in the standard form, it's pretty easy to figure out whether or not something's homogeneous. If q of x, so if the right-hand side is 0, then it's homogeneous. Otherwise, it is not homogeneous. Note that if it's nonlinear, then neither definition applies. So this is a definition that we're going to restrict to talking about linear ODEs. Occasionally, in some advanced classes, you might hear the term used in a more general setting, but we're not going to. So if it's nonlinear, then we're going to say it's neither. Let's give a couple examples of this. Let's say we have y double prime plus y prime plus y is equal to 5. This here is inhomogeneous because this right-hand side is equal to, well, not 0. But y double prime plus y is equal to 0. This, of course, is homogeneous. And lastly, you do have to sometimes rewrite things. So if you had y triple prime plus sine x y prime plus x squared y is equal to 5y, well, this you can rewrite into y triple prime plus sine x y prime plus x squared minus 5y is equal to 0. Ah, yes. So, let me finish this. So this one here is homogeneous. Now there's the question of why can't you turn the first one homogeneous? Like, so the question is why is y double prime plus y minus 5? So you can rewrite it that way, right? But now let's compare. So here this is the y double prime. So there is some y double prime over here. Here this y prime corresponds to the layer. This y corresponds to the layer. What does this minus 5 correspond to? So the standard way that we write this is we write all the things that have a y or a y prime on the left, and the things that without it on the right. And that 5 layer doesn't have a y component y multiplied by it, and so therefore it is inhomogeneous. Does that answer your question? So this here is still, these are the same, and so this is still inhomogeneous. So basically, when you're talking about a more formal way of describing it is when you have a linear ODE, it's some linear combination of your derivatives of y, y itself, and something that doesn't have any y component. So if something doesn't have any y component multiplied by it, then it is homogeneous. So you have to be a little careful because this is not quite the same as autonomous. Autonomous talks about whether or not you have x. Homogeneous talks about whether or not you have any components that don't have y. And so you can occasionally have things that don't have y, but are still, so like this equation here is autonomous, right? But it is still inhomogeneous. So you have to be a little careful there. And let me give one other definition. So this one should be fairly straightforward. Constant coefficient. So hopefully when you see that, you're like, oh, well, that probably means the coefficients are constant. And that would be correct. So a linear ODE has a standard form. If all the AIs of x are equal to some constant, then it has constant coefficients. Otherwise, it does not have constant coefficients. And note that if it's nonlinear, we're not applying this terminology. You can generalize this definition to nonlinear equations if you're careful enough, but we're not going to do that. So, a couple examples of this. Y double prime plus y prime plus 2y is equal to 0. Well, this has constant coefficients. Similarly, different, y plus 5x y prime plus y is equal to 0. Well, this is non-constant coefficients because you have this x here. Y double prime plus 5y prime plus y is equal to 5x. So this one's a little bit trickier. The answer to this one is this is still constant coefficients because we only care about the parts of it that also have a y. So this here doesn't matter for the constant coefficients. How is constant coefficients different from autonomous? Well, look at this last example here. This last example is not autonomous, right? Because you still have an x on the other side. And so there's still an x somewhere in here. And so therefore it's not autonomous. So it doesn't matter for constant coefficients. But this is still non-autonomous. I need to spell that correctly. Okay, why is the first one constant again? Because you can think of this as having a 1 here and a 1 here. And so the coefficients 1, 1, and 2 are our constants. Oh, what is autonomous again? Autonomous just means that there is no explicit dependence on x, or on your time variable. Whereas constant coefficients means that you don't have any for a linear ODE, constant coefficients means that there's no x dependence on the left-hand side, but you still might have x dependence on the right-hand side. Is that all right by everyone? So let's try this out to make sure we understand these definitions. So I'm going to, the last one here. Yes, the last one would be inhomogeneous. Yep. So let's try these out. Let's try out a bunch of examples. So let me reset the chat voting poll. Y prime plus 9y is equal to x squared. So is this, what is this? Does this have constant coefficients? Is it homogeneous or inhomogeneous? Okay, so we have most votes for inhomogeneous constant coefficient. Well, let's take a look. So this part implies inhomogeneous. These two imply constant. Oh, sorry, I shouldn't. Let's put a 1 there. So these two imply that it is constant coefficients. And so therefore, this answer is constant coefficients inhomogeneous. It's B. Okay, let's try another one. Y prime minus, let me reset before you guys start voting. Let's try y prime minus pi y is equal to 0. So is this homogeneous? Is it, does it have constant coefficients? Okay, so most people have answered homogeneous and constant coefficients. Well, why is that? So let's A. And that's because we have this here, so it's homogeneous. And you have a 1 here and a pi here, which are both constants, and so it's still constant. Okay, good. So you guys seem to have on the hang of it. Let's do a bunch more, and I'll do these a little bit faster. So is this one, what is this one? Y double prime? Oh, yeah, sorry. Y double prime plus xy prime plus y is equal to 0. So there are a couple questions to ask. The first is it homogeneous? And whether or not it's homogeneous depends on this right-hand side, right? So this is a 0, and so therefore this is homogeneous. The next question is, do we have constant coefficients? Look at this x here. We don't have constant coefficients, and so it is homogeneous but non-constant coefficients, and so the answer here is C. I don't get when it's homogeneous even with two variables. Ah, so is that the question about the second one? Or is that a question about the third one? Oh, the third one. Okay, so homogeneous is only talking about the stuff on the right-hand side. So if you rewrite it in the standard form where you have all the y derivatives and the y's on the left, and it's linear, and you look at the right-hand side, couldn't the x be moved to the right hand? Well, what happens when you try moving it to the right hand? If you were to move it to the right-hand side, you'd end up with y double prime plus y is equal to minus xy prime. But then, when you move it to the right-hand side, you've accidentally moved one of your y primes as well. And so you can't just move the x. When you try moving the x over, you accidentally move a y with it, and so therefore it is not. Therefore, it doesn't matter. So the trick here is that you have to be really careful about writing things out in this canonical form. So this, you have to write it out in such a way that all your y's and y primes are on the left, and then you need to make sure, anything that doesn't have a y or y prime is on the right. And that's how you can tell from this form. Does that help a little bit? Okay. Don't worry, we'll go through many more of these because this is important for you to understand. And hopefully I'm not boring the people who already understand this. So let's say we had y double prime plus e to the x y prime is equal to 3. Let me reset. Okay. To answer Sam's question, yes, it's because you can't separate the x and the y over on the third example there. Okay, so what do people think about this fourth example? Oh, okay, split vote. Let me wait a little bit longer and see what people think. So, okay, this is a really split vote. Okay, well let's look at this carefully. So the first thing we need to pay attention to is it homogeneous or inhomogeneous? Well, it is inhomogeneous, right? Because you have that 3 there. So it's inhomogeneous, which automatically means it's not C. And the next question is it constant coefficients? Well, the answer is no, it is not constant coefficients because of your e to the x here. And so the answer here is D, inhomogeneous and non-constant coefficients. Okay, let's do a couple more, since hopefully by the end you guys understand this. So let's try this one here. I'm going to reset. So what about this one? Is this one... so it looks like only one or two people have caught the trick. So I'm just warning you, there is a trick here. So pay attention. Okay, so more people are catching on now that I pointed out that there is a trick. So you should always be looking out for this when I do this sort of thing. And here, look at this y squared. This is nonlinear. And so, yep, it is nonlinear, and therefore none of these things apply. So be careful, because that might be something you see in an equation, and if you see that, then homogeneous and constant coefficients, we're just not going to apply those definitions at all. Okay, let's do another one. This one's also a little bit... I'm going to start throwing in ones that are slightly trickier. So what about this one? Okay, so you guys caught this trick. So the trick here was pretty straightforward. It's just, you can rewrite this as x double dot plus 4x dot plus 4x is equal to 0. And therefore, it's homogeneous with constant coefficients. Okay, and let's go on. So let me reset. What about this one? Sine of x, y double prime plus e to the x, y prime plus y is equal to 0. Okay, yep. So I didn't actually have a trick in this one. So this one is just homogeneous, non-constant coefficients. Let's do this one. So x, y double prime plus y is equal to x squared. So what do people think about this one? So there was a question that flew by in chat. Does the equation have to depend on x? So remember when we talked about independent and dependent variables. So if you think if you're thinking about these in terms of dy dx, this one down here, that's your independent variable and that's your dependent variable. And so that's how you should be thinking about this. And so if you're talking about dx dt, then all of a sudden that's your dependent variable and that's your independent variable. And so those are the variables that we care about. So normally, in standard notation, we talk about y being the dependent variable and x being the independent variable. And so then we're talking about all the derivatives of y. But if you're talking about x being your dependent variable and t being your independent variable, then you'd be talking about all derivatives of x, like you do in this example here. Okay, so it looks like I successfully double faked you out. So the trick here is that this actually is inhomogeneous, non-constant. So this here is D, because the nonlinearity here doesn't matter. So x is allowed to be nonlinear, just not y. And so the answer here is actually inhomogeneous with non-constant coefficients. Okay, let's do one last one. And make sure you watch out for any tricks as well. Oh, he already did it in the first question. I'm not sure what you mean by that. Oh, the x squared. Yes, I already did the x squared. Yep. So, okay, so what do we get? We got a bunch of b's. Okay, yep, you guys all caught the trick. So you rewrite this as y double prime plus 4y is equal to minus 4. And so therefore this is inhomogeneous with constant coefficients. Okay, good. You guys caught all of the last trick, but just be careful about this. You need to make sure that when you're solving these things, you rewrite it in the standard form. And if you don't do that, then, well, then some of the theorems we're going to be talking about later don't apply. Okay, so now that we've spent a lot of time on that, let's go on to actually trying to talking about some of the solutions to these equations. Now, the first thing I'm going to do is I'm not actually going to solve it. I'm going to give you a property of solutions to these equations. So, suppose you have some y1, which is a function of x. So let's say this is some function of x. And it is a solution to the homogeneous linear ODE with these non-constant coefficients. So these coefficients don't have to be constants. Then, in this case, if C1y1 is a solution to the same ODE where C1 is a constant, then C1y1 is a solution to the same ODE whereas C1 is a constant. So basically what we're saying is that if you have a solution to a homogeneous linear ODE, you can multiply it by some constant and you still get another solution. I'm actually going to give a proof of this. I know I don't give proofs very often in this class, but I'm actually going to give a proof of this since it's a fairly straightforward proof. So note that we can rewrite this as an times the nth derivative of c1 y1. So let's plug in c1 y1 into this thing. Plus a1, the derivative of c1 y1 plus a not c1 y1 is equal to 0, where these an's can be functions of x. It doesn't even matter. Well, we can rewrite this because when you take derivatives, you can just pull the constants out in front, right? So you can pull the constants out in front. And so since you can pull the constants out in front, this is equal to c1 times an, the nth derivative of just y1, a1 d dx y1 plus a naught y1. Well, and now note that this is a solution. And so since this is a solution, that means that solves this problem. So this entire thing is equal to 0, and therefore this is equal to 0. And that ends the proof. Okay? Let me give an example of this, and then I'll, if you still have questions about this, I can go into a bit more detail. So let's say y double prime plus 3y prime plus 2x is equal to 0. I'm going to tell you that y1 equal to e to the minus x is a solution. So this is a solution, and we can check this. So let's check y1. Well, if you check that, what you end up getting is e to the, what's the second derivative of e to the minus x? Well, the first derivative is minus e to the minus x, and the second derivative is then e to the minus x again. Plus, plus, when you take the minus 3 e to the minus x, plus 2 e to the minus x, and this is equal to 0. And so this is a solution. We can check it by just plugging these things in. But now let's check some constant multiple times. Let's check 5y1. I don't know why, but I really like the constant 5 today. Anyway, so if we check this, we plug that in, what you get is 5e to the minus x minus 15e to the minus x plus 10e to the minus x is equal to 0. And so that's also a solution. So basically, the whole reason we spent so much time talking about homogeneous ODEs is because when you have one solution, you can just multiply, and then you get then you get another solution. If you multiply by a constant, you end up getting more solutions. Any questions on that? Okay, great. So that's one thing you can do with the solution. What's another thing you can do? So you can also add together solutions. So if y1 and y2 are both solutions to this homogeneous linear ODE, then y1 plus y2 is also a solution. And the proof of this is basically the same. It relies on the fact that when you take the derivative of a plus b, that's the same as the derivative of a plus the derivative of b. And so if we write this out in the same way, an times d to the n dx to the n y1 plus y2 plus dot 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 plus a1 d dx y1 plus y2 plus a naught y1 plus y2. We want this thing to be 0, because if it's 0, then it's a solution. So we separate this out into two different pieces. One of them is just a1, the nth derivative of y1, plus dot 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 plus an y1 to the nth derivative, a1 y1 prime plus a naught y1, plus an y2 to the nth derivative, plus dot 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 plus a1 y2 prime plus a naught y2. Well, again, each of these two are solutions, and so when we plug those in, these have to be equal to 0. And so then this entire thing is equal to 0, which ends our proof. Let me give an example of this. So if we have y double prime plus 3y prime plus 2y is equal to 0, I'm going to give you two solutions. One of them is the one from before, e to the minus x. Another one of them is e to the minus 2x. So you can check on your own time that these two are actually solutions. But if those two are solutions, then we know that y1 plus y2 is also a solution. And the reason for this is when we plug in y1 plus y2, what you get is e to the minus x plus e to the minus 2x, the second derivative of that, plus 3 times e to the minus x plus e to the minus 2x, and we want the first derivative plus 2 e to the minus x plus e to the minus 2x. And when we write all of that out, that's equal to e to the minus x plus 4e to the minus 2x. So you should take these derivatives and double check this. Minus 3e to the minus x minus 6e to the minus 2x plus 2e to the minus x plus 2e to the minus 2x. And this entire thing is equal to 0. And that brings us to a very, very important theorem for homogeneous, for homogeneous ODEs, for homogeneous linear ODEs. So if you have a homogeneous linear ODE, and you have of order n, so there's an nth derivative here, and we have n different solutions, then by the principle of superposition, which is what we just proved, then you can get a bunch of other solutions by just taking c1y1 plus c2y2 plus dot 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 cnyn is a solution to the same ODE where ci are arbitrary constants. Okay, so if you can find n, and this is actually a big part of a bigger theorem, which we're not going to prove, if y1 and yn through yn are linearly independent, then all solutions to the ODE can be written in this form, c1y1 plus c2y2 plus dot 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 cnyn. So we can call that the general solution to the ODE. If there's multiple solutions, can you only add two of them together and get another solution? Yes, absolutely. You can only add two of them together, because you can have, if you think about it in this general solution form, you can also set one of the c's to be 0. So if you set c1 equal to 0 and c2 equal to 0, then you're just adding together c3y3 all the way through c and yn. So yes, you can add together any combination of solutions and you get another solution. You can multiply a solution by some constant, you get another solution, and you can do this as much as you want. And the other important part is that every solution, assuming y1 through yn are independent, which let me remind you of the definition. So recall that independent means that c1 y1 dot 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 plus cn yn is equal to 0 only if all of our c1s are, all of our c's are equal to 0. Okay, so this is the same idea of linear independence as we dealt with vectors. And so now the big point here is that you can, sorry, my lighting's going weird. Let me try fixing that. Okay, that's a bit better. sun went away. So can it be y1 plus y5 plus y7? Absolutely. So you can have any combination of these, and these are all solutions. No, but you have to be really careful. You can't ever multiply together solutions. y1 times y2 is not a solution. Can the constants be any constants? They can be any constant number. Yes, they can be 0, they can be pi, they can be minus 50, they can be minus the square root of 2 plus 3. So yes. So the constants can be any constants that don't have any dependence on the variable. Okay, so this is very important because this means that we're going to be able to solve problems in general. So I'm going to give you a formula. I'm going to sort of prove the formula, but I'm just going to give it to you. And so note that we weren't talking about constant coefficients a moment ago. We were just talking about general homogeneous ODEs. So now consider the case where these are all where all the coefficients are constant. If all the coefficients are constant, we can write a characteristic polynomial, an r to the n plus dot 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 a1 r plus a naught. And if pi is a root of the polynomial, so that is to say pi of, sorry, not pi, lambda. So if lambda is a root of the polynomial, that is p of lambda is equal to 0, then e to the lambda x is a solution. If it's a root with a higher multiplicity, so if it shows up multiple times as a 0 of your polynomial, then x to the k minus 1 e to the lambda x is a solution to the ODE. Why we just switched y with r? Yes, we just switched y with... So you have to be careful. We didn't switch y with... exactly switch y with r. We switched derivatives of y with powers of r. So the nth derivative of y and the nth power of r. So that's how we wrote this new polynomial. And then I'm just going to say that lambda is a root of this polynomial. So p of lambda is equal to 0. So as a brief preview of something we're going to talk about probably next week, maybe the week after, we'll often call lambda an eigenvalue of the ODE. This is for reasons that will become clear later. This has the same sort of... this is closely related to the eigenvalues of a matrix for reasons that we will go into later. So in case I accidentally use that term, just try not to be confused. So let's give some examples of this. Let's give an... Oh, wait, what just happened? Why did my example... Oh, I guess I must have deleted my example. Well, that's all right. I'll write one out. So let's say that we had y double prime plus 3y prime plus 2y is equal to 0. Okay, so now we have p of r, so our polynomial, is equal to r squared plus 3r plus 2. And we want p of lambda to be equal to 0, so that's equal to r of lambda squared plus 3 lambda plus 2. And therefore, 0 is equal to lambda plus 1 times lambda plus 2. And so lambda is equal to minus 1 or minus 2, plus e to the minus x and e to the minus 2x are solutions. And so in fact, the general solution is c1 e to the minus x plus c2 e to the minus 2x. Okay, let's do another one. So let's say we had y double prime plus y 2y prime plus y is equal to 0. Well, then p of r is going to be equal to r squared plus 2r plus 1. So p of lambda is going to be equal to lambda squared plus 2 lambda plus 1 is equal to 0. And therefore, lambda plus 1 squared is equal to 0. So lambda is equal to minus 1 with multiplicity 2. So it's a multiplicity 2. Why does the 2 not get a lambda? So when you're converting these, you're taking derivatives of y. So the second derivative of y corresponds to the second power of lambda. So when you just have a single derivative, that corresponds to a single lambda. But when you have just y is the 0th derivative of y, right? You aren't taking any derivatives. And so therefore, you have lambda to the 0, which is equal to 1. But going back to this one here, so we have y is equal to minus 1 multiplicity 2. So then e to the... No. So let me explain it. Let me try again in a moment. Actually, no. Let me try again now. So let's say let me rewrite this. Let me finish solving this, and then I'll go back to that. So e to the minus x and x to the e to the minus x are solutions, and so therefore c1 e to the minus x plus c2 x e to the minus x are solutions. So there are a couple different questions in chat. So let's address them one by one. We can rewrite this. I'm going to rewrite this in a sort of weird way. I'm going to rewrite this as d squared dx squared y plus d dx y plus 2y. Okay? So hopefully I can convince you that this is another way of rewriting y double prime plus 3y prime plus 2y. And what we're doing here is we're replacing d dx with r. Okay, so we're thinking about the derivative operation as the thing that we're replacing with r, and then we're getting rid of the y's. Okay, hopefully that helped a little bit for Sam. Let's see, Jordan, what does multiplicity 2 mean? So that means that when you take a polynomial, the roots of it are the values that you get when you get 0, right? Why do you get rid of the y's? So there is two different answers to that. The first one is we're defining some new polynomial, and so we can define it however we want, and we just happen to define it without the y. The second part of it is that you could think of this as a polynomial where if you have a y layer, another option is if y is just equal to 0, right? So if you think about this, let me write this. If you think about this, you could include the y layer if you wanted to, and then when you set this equal to 0, you either get that lambda is equal to -1, lambda is equal to -2, or y is equal to 0. But y equal to 0 is always a solution, and so we don't really care about that. And so that's why we don't care about the y equal to don't care about the y's. Okay, so why do we let's see, what does multiplicity 2 mean? So multiplicity 2 means that it's just when you factor out your polynomial, each of the various factors contributes a 0, right? So here we factored here, so this contributes lambda is equal to -1. This contributes lambda is equal to -2, right? But here, let me rewrite this actually. If we rewrite this, this is lambda plus 1 times lambda plus 1 is equal to 0. So this contributes a -1, right? But this also contributes a -1, and so you have two different -1s when you're talking about roots of this polynomial. And that's what it means when you have multiplicity 2. So when you factor it out, a root has higher multiplicity if it appears multiple times. Does that answer your question, Jordan? Okay, so let me spend a little bit more time and try to give you an intuitive idea about why this is true. And this might help Sam a little bit as well. So I'm not going to formally prove this because that would involve like properly explaining what differential operators are, but we can sort of get the intuition. So y double prime plus 3y prime plus 2y is equal to 0. Okay? I'm going to rewrite this in terms of differentials, in terms of taking derivatives, these operations. So d squared dx squared y plus 3 times d dx y plus 2y is equal to 0. Now the next thing I'm going to do is I'm going to factor this out. So I'm first going to factor out the y. So d squared dx squared plus 3d dx plus 2y is equal to 0. Now this is a little bit weird. This is well defined, but it's not something you've seen before. We've never split d squared dx squared from the y or d dx from the y, but we're going to do it that way. And there is a way you can make this formally rigorous, but we're not going to do that. So now when you do it this way, you can think about factoring out this in terms of d dx. So this is d dx plus 1, d dx plus 2, y is equal to 0, right? Or you can factor it the other way, which would get you d dx plus 2, d dx plus 1, y is equal to 0. Okay, so now the next thing we're going to do is I'm going to show first prove something. So note that if you note that these are all d dx, d over dx plus some constant. In fact, they're d dx plus some root of the polynomial. So I'm going to say d dx plus lambda y is equal to 0. If we're trying to solve that, then if why is it plus 1 and plus 2 now? Because if you think about, if you replace that with, say, r, you get r squared plus 3r plus 2, y is equal to 0. And so you just do a factor. You just factor that out and solve it as a quadratic. Okay, so you can use binomial expansion and expand that back out, and you get back the original equation. But now let's try to solve d dx plus lambda of y is equal to 0. Well, so let's put the y's back in. So you have dy dx plus lambda y is equal to 0, and so therefore dy is equal to minus lambda y dx, and so then dy over y is equal to minus lambda dx. You integrate both sides, and you're left with natural log of y. Absolute value of y is equal to minus lambda x plus some constant. So that absolute value of y is equal to c e to the minus lambda x, where c is positive. And so therefore y is equal to c e to the minus lambda x NEC. Can you re-explain what you did after you factored it? Oh, so I haven't done anything to it yet. So I'm just giving you a note. So this is an aside. So this is if you're familiar with math terms, this is a lemma. So I haven't done anything with it yet. I'm just written out this lemma. So I factored it now, right? So now we want the entire thing, going back, we want this entire thing here to be equal to 0, right? So we want the entire thing, we're about to use it. So we want the entire thing to be equal to 0. What's one way of getting the entire thing equal to 0 is to get just this piece equal to 0, right? So if we just get just this piece equal to 0, then the entire thing would be equal to 0 because you're multiplying some operator by 0, and so then you get 0. So when we're doing that, that implies this blue dot here, you can substitute that in. So there, lambda is just equal to 2, right? So therefore, you know that y1 is equal to c e to the minus 2x for some constant c. And if we do the same thing over here, where we've rearranged the order of our factoring, you end up getting that y2 is equal to c e to the minus x. So this is just basically giving you an idea of how we proved this big theorem here. So we obviously haven't proved all of it, but this is basically the idea behind the proof for why this works. And we just used the lemma a moment ago when because we wanted to set this thing equal to 0. Okay, so now you don't need to understand the details behind this proof. So like per usual, I don't expect you to understand any proofs in this class. I'm just giving them to you to try to explain some of the intuition, so hopefully it makes a bit more sense. Let's try it out. So, which of the following are solutions to y triple prime minus 2y double prime minus y prime plus 2y is equal to 0? And let me reset the chat. So, of course, the first thing you need to do is you need to write the characteristic equation, which is going to be y cubed minus 2y squared, lambda cubed minus 2 lambda squared minus lambda plus 2 is equal to 0. And then you're going to have to factor this out. And I'll go ahead and give you a hint. The very first step of factoring it is lambda minus 2. And if you factor this, you get lambda minus 2, lambda squared minus 1 is equal to 0. And hopefully you can keep on factoring from there, and then tell us which of those solutions is the solution. Let me give you another step. So you have lambda minus 2, lambda plus 1, lambda minus 1 is equal to 0. So therefore, lambda is equal to minus 1, 1, or 2. So what are the basic solutions here? Okay, so we've gotten a couple of these. So let's take a look. So what are the basic solutions? Our fundamental self-solutions is e to the minus x, e to the x, and e to the 2x, right? But of course you can add these together. So your general solution is c1 e to the minus x, c2 e to the x, plus c3 e to the 2x, and therefore all of the above are solutions. And it looks like people, yeah, okay. So yes, all of these are solutions, including the first two, because you can just set c equal to 0 for a particular correct appropriate constant. Okay, let's try it out one more time, and then we'll probably end here. So we aren't going to get to complex solutions today, but let's start out by, so I'm going to ask you this one here. What's the general solution to y double prime plus 4y prime plus 4y is equal to 0? Note that I am asking specifically for the general solution, not just any solution. Okay, so it looks like we have a lot of C's and a couple A's and B's, it looks like. So let's solve this. So what's the characteristic equation? So we have lambda squared plus 4 lambda plus 4 is equal to 0. Therefore, we have lambda plus 2 squared is equal to 0. And so therefore, lambda is equal to minus 2 with multiplicity 2, because this was a square here. And due to that, we know that e to the minus 2x and x e to the minus 2x are solutions. And so therefore, the general solution is c1 e to the minus 2x plus c2 x e to the minus 2x. Okay, and let's finish off with an initial value problem, and then we'll end for the day. So what's the solution to the initial value problem given by y double prime plus 4y prime? How do you get the second solution with the x in front? So that was part of the, so I didn't prove this, but that was part of the main theorem that I gave you. Wait, this theorem here. So if lambda is a root with multiplicity k, then x to the k minus 1 e to the lambda x is also a solution. I'm not going to prove it. If you want, I can point you at some resources proving that. But basically, when you have a root multiple times, then you just add x's in front of the previous solution. Okay, and so now what's the solution to this initial value problem? Note that I have given you two different things for the initial value problem because this is a second order differential equation, and so you need two initial conditions. And since I am completely out of time, actually, I'm going to go ahead and write this one out, and I might come back to this one later, just at the start of the next class. So y of x is equal to c1 e to the minus 2x plus c2 e to the x e to the minus 2x. And so therefore, y prime of x is going to be equal to minus 2c1 e to the minus 2x minus 2c2 x e to the minus 2x plus c2 e to the minus 2x. Okay, so that's just taking the derivative. And then we need to solve for that. So we have 1 is equal to y of 0. When you plug in 0 into y of x, you get c1 plus c2. And 2 is equal to y prime of 0, which is equal to minus 2c1 plus c2 when you plug that in. And together, this implies that c1 is equal to minus 1/3 and c2 is equal to 4/3. And so therefore, you have y of x is equal to minus 1/3 e to the minus 2x plus 4/3 x e to the minus 2x. Oh, yeah, sorry, I forgot to reset there. But it's the end of class anyway, so you can go ahead and put that in chat. It'll be a free participation point. But anyway, I should probably end the recording here. And yeah, thank you very much. I have office hours now, so if you have any questions, just stick around.